Hey there, today we're going to look at 4.04 series and sigma notation. And here's our goals. Represent a series with sigma notation, giving the sum in expanded form, and determine the sum of a series given the sum in sigma notation. So what is a series? A series is the sum of consecutive terms of a sequence. The sum of the first n terms of a series is called the nth partial sum. So in the sequence we see here, 11, 17, and so on, the sum of the first four terms is represented as 11 plus 17 plus 23 plus 29. This is a series because it's the sum of consecutive terms in the sequence. So adding those four terms together is called the fourth partial sum, and you will see it represented as S sub 4. This is something you're going to see, and this is even how a question could be asked. They could say, find S sub 4, and you would need to know, okay, that means add the first four terms of the sequence. When a series has many terms, it can be convenient to use sigma notation, also known as summation notation, sum, adding. Sigma notation uses the Greek capital letter sigma, which is what you see here. You also see it right here. So let's go ahead and break down all the parts of it. We have the first value of n on the bottom. They tell you the last value of n on the top. Okay? The n over here, they call the index of summation, but it's also just the variable. And over here is the formula for the terms. Now, we're going to practice putting this all together and using it, but let's go back to what it's used for. Okay? It's used to add a series of numbers that has many terms. Okay? So let's also get familiar with this vocab. The lower limit is the number you see below sigma down here. And it represents, like we said, the first number you plug into the formula. So first value of n means first value you plug into the formula. So we're going to start by plugging in 1. And the 6 on top is the upper limit. Okay, that represents the last number you plug into the formula. So to find this sum, you're going to start by plugging in 1. 4 times 1, obviously 4. And then you're going to plug in 2, and then 3, and so on until you hit the upper limit, which is going to be 6. Okay? So here we have an example of sigma notation with all of the steps worked out. Okay? So let's take a look. We have our variable is not n this time. That's fine. It's k. Doesn't matter. And the formula is different. It's k squared here. Here it was 4n. Okay? The formulas will change, but it looks like the lower and upper limits are the same. So what do? We start by plugging in 1 right here, 1 squared. Then we plug in 2, 2 squared. Again, all the way up until we plug in the upper limit of 6. And you're not just going to square each of those terms, you're going to add them all together. And when you do that, you get 91. Okay, so this is expanded form. If we go back to our goals today, it says represent a series with sigma notation given the sum in expanded form. This is expanded form, right? So what you see over here is a very shorthand way of showing the same thing. So what is the series in expanded form? This is your time to shine. Give it a try, and then find the sum. Okay, expanded form. Let's see how you did. We're going to start with the lower limit of 1. So 2 times 1 plus 3. And in the past, by the way, you know I to be imaginary numbers. Here, clearly, they're showing us the variable is I, so it is not an imaginary number. It's the variable. So this is going to give us just our first term, okay? And we want to take that entire thing and add it with the second term and so on. So I would advise you to put the entire thing inside parentheses. That way nothing gets confused. Okay, we need to follow the rules of PEMDAS. So let's do it. We're going all the way to 6. So I'm substituting 2 and then 3 all the way to 6. And I have to continue on the next line. So the first question asks, what's the series in expanded form? There it is. Now, what's the sum is a different question. We need to actually do the work. So let's just say that's question A. And now let's do B. Okay. 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7. We get 6 plus 3, which is 9. And very quickly, we can start to see the pattern, can't we? We're adding 2 every time. So at this point, could you continue with all of this? Sure. But I could also just add 2 every time until I get 6 terms. 1, 2, 3, 4, 5, 6. And just to be careful and confident, let's check the last one. 6 times 2 is 12, plus 3 is 15. We got it. Okay. Now we actually want to add those up. Let's see if I can quickly do this in my head. That's 12, 21, 32, 45, 60. I believe it's 60. If I calculated incorrectly, then you can double check that. But that's how we find the sum of the series given sigma notation. Clearly, you can see this is shorthand because there's a lot more writing going on here. But what about this one? Can you write this series in expanded form and find the sum? Once again, I'm going to pause. Actually, I'm going to ask you to pause and give it a try. All right, let's see if you got it. And by the way, I just double checked this. It is 60. So we're all good there. For this one, I'm gonna show you the work. So here it is. Hopefully you got it. Plugging in the lower limit of 3, right? We start with 3 and we go until we hit the upper limit of 5. So we plug in 3 and then 4 and then 5 and then stop. That's it. Only 3 terms this time. By the way, you want to be very careful. You're going to be asked questions like, how many terms are there in this series? If you start with 3 and you go to 5, I would suggest being very careful. Maybe solve a step here or at least write it out. Okay, I'm going to include 3, then 4, then 5. That means I'm adding 3 terms. Because I'm telling you right now, mistakes happen all the time with this. But back to our problem. It's PEMDAS, right? Solve what's inside the parentheses. Apply the exponent. And we do that here. We square these 3 terms. Then we combine with subtraction to get negative 450. All right, what do we have next? To write a series in sigma notation. Ooh, interesting. This time they're switching it up. We're doing the reverse. They're giving us the series and they're asking us to come up with sigma notation. First, determine whether the series is arithmetic or geometric. Okay. Then use the explicit rule for arithmetic or geometric sequences to identify the rule used in sigma notation. Then they want more, identify the lower limit, index, and the upper limit. So basically, come up with sigma notation. Let's start with the first part, breaking this down piece by piece. Okay, first determine whether the series is arithmetic or geometric. Let's take a look. One quick way to tell is, are the numbers growing or decreasing rapidly? No, they're not. So there's a good chance this is arithmetic. I'm going to write that down because I think that's what it is. Let's see. When I go from here to there, I'll do it down here. -4, -4, -4, and -4. Yes, it is arithmetic. There is a common difference we just found of -4. But remember, common difference can also be found by taking any term in the series and subtracting it from the previous term. So you can find D by taking 52 and subtracting the previous term, 56, -4. Okay, we've determined that it's arithmetic. They want the explicit rule. Okay, explicit rules. I gave you a little help there. They're in the bottom right. We know we're dealing with arithmetic. So we have a sub n is a sub 1. We see it here, 56. And sorry, I'm forgetting. They want explicit rule. Yes, for arithmetic. So plus, we have n minus 1. That does not change. And we found D. There it is. But we want to actually simplify this rule always, always. Maybe a good idea to put parentheses there too. Let's fix that up. There we go. Distribute, distribute. We get 56 minus 4n plus 4. Combine like terms, we get a sub n equals 60 minus 4n. That is our simplified explicit rule. Okay, did we accomplish the goal? Use explicit rule to identify the rule used in sigma notation. Interesting. So what did they just tell us there? Let's write our sigma notation out. They just told us that rule is our formula. So 60 minus 4n goes right there. It's all coming together, isn't it? Okay. Then identify the lower limit, index, and the upper limit. How would we do that? Take a look at your series. According to what we see, we're starting with the first term. No one told us anywhere that 56 is not the first term of the series, so it's safe to assume it is. And I don't see any numbers after this. I see a big fat period right there, so I think that's the entire series, and it is. So we count them 1, 2, 3, 4, 5. That means upper limit of 5, and there is the sigma notation they wanted. Interesting, interesting. When different things we learn come together. Fractions. We love fractions, right? Let's do it. Write the series in sigma notation. We just did this a moment ago. Can you do it by yourself? I believe in you. Do you believe in yourself? You should. Give it a try. How did we do this? Think back. What was the first step? If you're stuck, the first step was determine, is it arithmetic or geometric? Okay, and it could be confusing with all the fractions. I don't know. So try something. To find common difference, you take any term and subtract it from the previous term. To find a common ratio, you take any term and divide it by the previous term. So what do we get here? 1/5 minus 1? Well, we'll get back to that because I want to make sure we remember the rule here. The rule here is keep, change, flip. Well, 1, so we're going to keep, change, flip. Well, 1 is just 1, right? The same as 1/1. So that stays the same. So what is that? 1/5 times 1 is 1/5. That's what we have, isn't it? So we don't even need to worry about the common difference. And we get common ratio, meaning it's geometric. So let's use that explicit rule. A sub n is a sub 1, first term we see, times r, we just found it, to the n minus 1. Where does this go? Who remembers? I hope you do. We get our sigma notation, and that is our formula on the side. But 1 times 1/5 is just 1/5, right? So we could just write 1/5 to the n minus 1. Again, they didn't tell us there are any terms prior to 1 or after 1/3125. So we're going to use the same variable we used before, which is n, and we're going to count 1, 2, 3, 4, 5, 6 terms, upper limit 6, and there it is. Did you get it? I hope so. Let's keep practicing. Just a little more. Write the series in expanded form and find the sum. Write the series in sigma notation. This is very repetitive at this point. It's practice. So once again, I'm going to ask you to give it a try, and then I'll show you the work. And if you're not pausing this recording as you go and practicing this, I would highly recommend going back and doing that. Okay, on the left, series in expanded form is right there. Okay, start with 1. Keep plugging in until you get to the upper limit of 4. Multiply, add within each set of parentheses, and then add those together. And write the series in sigma notation. Hopefully you determine that it is arithmetic. That's clear to see. We're just adding 2 every time, so D is 2. We grab our explicit rule, simplify that formula on the side. Now we still start with 1, but there are quite a few terms here, so the upper limit is a little bit bigger. It's going to be 9. Okay. Write sigma notation for the series for both of these. Okay. Reminders of how to do this. Formulas on the bottom. Let's see how you do. Okay, on the left, we have geometric with a common ratio of r. Again, if you weren't sure, you could start by finding, okay, D would be 15 minus 3. R would be 15 divided by 3. And what does this give you? 12. Are we adding by 12 every time? The first time, yeah, but no, not after that. So again, common difference is out. Here, you get 5, meaning common ratio is 5, meaning we're multiplying by 5 every time. Okay? Multiplying by 5 every time. So we get geometric ratio is 5. We get our explicit rule. Plug it in. Notice, do not multiply that 3 and 5 together. It's super tempting, but remember PEMDAS, right? When you plug in that 1 in the numerator, you will need to apply 5 to that power first and then multiply, right? P comes before M in PEMDAS every time. All right, ready for the next one? Let's see how you did. Geometric. Once again, anything interesting to note? I would say finding whether it's geometric or arithmetic is very important. So let's focus on that. D, common difference would be 144. I'm running out of space. I'll do it over here. It would be 144 minus negative 288. That would be a big positive number, right? You'd be adding these two. You would not get negative 72. So right away, you know it's not D, but R. And let's do that. R is any term divided by the previous term. Those are big numbers, but we can see that is negative 1/2. You could always use your calculator too if you're not sure. Again, do not multiply these two together. Keep them separate. Okay, and we count. There are 8 terms. Upper limit's 8. There it is. And that, my friends, is the end of today's lesson. Okay, don't forget to study, practice, and take the quiz when you're ready. I'll see you next time.